Okay, so for part A, it asks us to draw a free body diagram. So there'd be the force of gravity pulling the ball down, and the normal force pushing against the ball, the surface pushing against the ball. Since it's sloped, it would be something like this. If we were to take it at this point. And the normal force would be greater than the force of gravity, since it doesn't move in the y direction. Part B, the question asks to derive an expression for f of n. So the net force in the y direction is equal to 0. So and say the angle that we took was from the top. So theta is from the top, so that means cosine would be the vertical and sine would be the horizontal. So we would get f of n cosine is equal to mg. And we just isolate for f of n, and we get f of n is equal to mg over cosine theta. Theta isn't in the given variables or the given terms, so we want to rewrite the expression. So cosine is just equal to adjacent over hypotenuse. So the adjacent side would be d, and the hypotenuse would be r. So we just substitute in the values, so then we have and we get this because we have this fraction on the bottom, and we can rewrite the fraction by multiplying r to the top. For part C, it asks to prove the tangential speed. So we'd be looking at the horizontal. F of c is equal to f of x, and f of x would be sine theta here. We derived an expression for f of n, so we can just plug that in. And we isolate for where these m's cancel out, and we just isolate for the velocity. And there's no theta in there, so we can find that sine is equal to opposite over hypotenuse. We can just plug that in here. So we'll have the opposite would be r over r, opposite over hypotenuse. So if we multiply, these r's would cancel out, and then this r would become squared. So what we're gonna have is b squared is equal to g r squared over d. Now, in the equation, it's written r squared minus y squared. So we know that the hypotenuse is c squared plus ab squared. So r squared is equal to, and we isolate for r, and we get and we can plug that in here. So we have v is equal to g and we isolate. The FRQ is in terms of y, and I'm assuming that d and y are the same length, so that d is equal to y. So I'm just assuming that you can just plug in y here. So okay, so for part D, it asks us to derive an expression for the angular velocity of the ball in terms of r and y. So v is equal to r omega, and we can use this expression here that we found and substitute this in. And we isolate for omega. And we found what r squared is equal to here. So substitute that. And these would cancel out. So we have omega is equal to root. But it wanted it in terms of y. So we know that r is equal to d plus y, since these are both half of this. Isolate for y, and we have isolate for d here. We have r minus y, and that's the variables that the it wanted it in. This is g and this is y. For part E, it wants the minimum angular speed. So we found the angular speed expression here. And for the value to be at its minimum, the denominator has to be the greatest value that it could possibly be. So the larger the denominator is, the smaller it would make the omega value. So for the value y would have to be equal to 0 for omega to be at its smallest, since these two are just constants. So then we find that omega minimum is equal to, and to match the expression given in the FRQ, we just multiply, and then we'll get For part F, we're asked to find the RPMs. And we're given a value here. And assuming that D and Y are equal to each other, Y would just be R over 2. Since it's just half. And we just plug in values, we'll get 9.89 rads per second. And we just have to convert this to RPM. So we would just multiply by 60 over 2 pi. So the seconds converted into minutes and the rotations. And we will get a value of 94.44 RPM. For part G, it asks to derive an expression for the period. So speed is equal to distance over time, but if we convert it to angular, it's omega is equal to distance, which is the circumference, which is just 2, or not the circumference, it would be in radians. So 2 pi over the period. And we know what omega is equal to, so we can set this to what we found earlier. And we'll get 2 pi over the period is equal to root G R minus Y. And we just isolate for period, multiply and divide this. Multiply and divide this. And we'll just get period is equal to 2 pi. So for part H, if the ball is now rotating instead with an angular speed omega about its axis of symmetry, find the angular speed needed to keep the ball rotating with the ball. So that means that for the force, the centripetal force would have to be equal to the normal force in the x direction. We found Fn to be mg over cosine theta, so we can just plug that in. It wanted the angular speed, so we can break down the velocity, the v, into r omega. This would cancel out with the exponent. The m's would cancel out. So we have v squared r g over. Now we could make this tangent since sine over cosine is tangent, but this r isn't expressed in the given variables. So if we break down sine into its components, which would just be r over r, we could cancel out this r with that one, and we'll have this r in the denominator. Sorry, this would be omega. So isolate from omega, we just square root both sides. G over cosine. Cosine theta r.